Another question from Abhijit Datto. Any special difference for hydrogen atom problem?
No. Difference in the scheme is the same thing. Only thing is that we will actually solve it here, the radial part, and that too also radial part we rescale with some u r by r, right? R into r, right? That way I write u. Okay, so that way you have the final differential equation, and you have to either you can directly put the values from your repository. You have all the natural constants in your NumPy repository, right? In module, there is a module called constants. You can actually import value of electron charge, mass, Planck's constant, h bar, everything you have there. So you blindly write the equation, discretize it, and put Yeah, I'm back. We can discuss it later. I mean, you can directly put the constants, or you can rescale it in such a clever way that the solution you can find the energy from the searching. Which energy domain you will search, that will understand. Otherwise it's okay. Scheme is same. Okay, you please try. I'm also have a lot of time on this. Okay, I think Ananda should start now.
Yeah. We pass on to the next speaker. Ananda, please start your discussion. Thank you.
Okay, so let me just present. Okay, first, I'm taking over from Abhijit Kaurgupta right now. Okay, I think this will. I hope it allows me to override him. It should. Okay, so first, before I start, I must thank Abhijitda for taking most of the hard things out of my way. But I'm going to talk about some difficult things today, so maybe it's all good that most of the really difficult stuff has already been handled. But before I start my actual presentation, I am a bit, আমি এটা লোভ ঠিক সামলাতে পারছি না। সেটা হচ্ছে এই যে আমি যেহেতু এখন কোয়ান্টাম মেকানিক্স পড়াই আমার ইনস্টিটিউটে, তার ছাত্রদের দেখানোর জন্য আমি একটা প্রোগ্রাম লিখেছিলাম, সেটা পাইথনেই লিখেছিলাম। এক্স্যাক্টলি অভিজিৎদা যে মেথডটার কথা বলছে সেটাই, প্রোগ্রামটা নয়, এটা তার ডেমনস্ট্রেশন বলতে পারেন। ডেমনস্ট্রেশনটা মোটামুটি এরকম না, এটা হচ্ছে বেসিক্যালি ওই ওরিয়েন্টিন দিয়ে না, এটা পাতি অয়েলার দিয়ে ইন্টিগ্রেট করে করা, একদম সবচেয়ে সোজা মেথড, যাতে আমাদের ছাত্ররা নিজেরা লিখতে পারে, যারা এখন সাইপাই শেখেনি ইত্যাদি। মানে এখানে শুধু একটা স্লাইডার আছে, এই স্লাইডারে দিয়ে যদি আমি এনার্জিটা পাল্টাই, দেখুন যেটা হচ্ছে আমি যখন এনার্জিটা নিচ্ছি এরকম একটা ভ্যালু 4.9, এটা হচ্ছে হারমনিক অসিলেটর পোটেনশিয়াল। তার এনার্জি আইগেন ভ্যালুগুলো এই স্কেলে হচ্ছে 1, 3, 5, 7 এরকম করে অ্যাকচুয়ালি। তা যদি 5-এর থেকে খুব অল্প কমও হয় আমার এনার্জিটা, দেখতেই পাচ্ছেন আমার ওয়েভ ফাংশনটা যেমন এখানে 0 থেকে শুরু করে আমরা গিয়েছিলাম একদম ওই সেকেন্ড এক্সাইটেড স্টেটের মতোই একটা ওয়েভ ফাংশনের মতো করছে বটে, কিন্তু এখানে এসে ওই 0 দিয়ে যাওয়ার বদলে ইনফিনিটির দিকে চলে যাচ্ছে। তো বেসিক্যালি ট্রাইং টু ডাইভার্জ। তার সহজ ম্যাথামেটিক্যাল কারণটা হচ্ছে এখানে দুটো সলিউশন আছে, একটা ডাইভার্জিং, একটা কনভার্জ করে। ইনফ্যাক্ট দুটোই ডাইভার্জ করে when lambda is not exactly equal to 5, and here you are getting a divergence. But if I change the slider slowly by just dragging it across, and যেটা হচ্ছে যে এই যে আমি এটাই কিন্তু অ্যাকচুয়ালি বাইসেকশন মেথডে যেটা করা হচ্ছিল, বেসিক্যালি এইটাকে অন্য মাথাটাকে 0-র দিকে যাওয়ানোর চেষ্টা করা। দেখুন এটা যেই 0-তে মিলে গেল, এখানে উত্তরটা আমি জাস্ট একটু ওভারশুট করে গেছি অ্যাকচুয়ালি, কিন্তু তাহলেও প্রায় এক্স্যাক্টলি 5 এর কাছাকাছি গিয়ে অন্তত মানে 5টা ডেসিমাল প্লেস যদি 5 এর কাছাকাছি গিয়ে এই আউটপুটটা ওদিকে 0-তে চলে যাচ্ছে। এটা একটা খুব সোজা প্রোগ্রাম, মানে বিশেষ কিছু নেই এতে, কিন্তু যেই আমি পেরিয়ে গেলাম আবার উল্টো দিয়ে চলে গেল। এই প্রোগ্রামটা দিয়ে ম্যানিপুলেট করে কিন্তু ছাত্রদের অনেক কিছু, এই যে কোয়ান্টাইজেশন কেন হয়, কেন why exactly do you have specific values of lambda or specific values of energy at which you get a physical wave function. These things can be demonstrated very easily with a program like this. The program essentially is exactly what Abhijita talked about. Except that I'm not doing bisection here, I'm just using a slider and dragging the slider across so that I can get, as I change the slider, I can see how the wave function changes. But the aim is essentially the same. The aim is to solve for the fact that at the other end, that is, I start with 0 at this end, I want to ensure that at the other end, I'm going to get 0. And that is what I'm trying to do. This was, of course, এটা একটু অনধিকার চর্চা হয়ে গেল। এটা অভিজিৎদা যেটা বলেছিলেন সেটাকে আমি এটা গ্রাফিক্যালি দেখানোর চেষ্টা করছি প্রসিডিওরটা। অফকোর্স অভিজিৎদা যেটা করেছেন সেটা হচ্ছে আমি এরকম একটা ভ্যালু নেবো যাতে এটা পজিটিভ হয়, তবে এরকম একটা ভ্যালু নেবো যাতে এটা নেগেটিভ হয় এদিকটা। এইবার আমি এই যে দুটো ভ্যালু অফ ল্যামডা পেয়েছিলাম বা এনার্জি পেয়েছিলাম, যার একসাথে পজিটিভ হয়েছে, এটা নেগেটিভ হয়েছিল, এবার বাইসেকশন বা কিছু করে এটা যাতে 0-তে আসে বা 0 খুব কাছে আসে তার চেষ্টা করবো। আচ্ছা, এইবার আমি আমার যেটা আসল বক্তব্য সেখানে শুরু করি। আচ্ছা, সবাই স্ক্রিনটা দেখতে পাচ্ছেন তো এমনিতে আশা করি? দেখা যাচ্ছে?
Yes, yes.
Okay, thank you. So let me now start the actual topic on which I was supposed to talk, which is solution of the time-dependent Schrodinger equation. Sorry, even the heading is wrong. I keep on making a mess of this. The heading should be time-dependent Schrodinger equation, how you would solve this. And this is a difficult problem. Okay, this is perhaps the most difficult problem which is set to students at this level. And as a result, what we are going to do is we are not going to take a look at all the very advanced, complicated things that people do to get a very good result out of this. We will try to use only simple-minded algorithms, the simplest possible. As it will turn out, the simplest possible algorithm will not be a very good one. So we will have to move away from the simplest possible algorithm and go to something slightly trickier. But we will not try to go to, say, state-of-the-art things here. That's simply way too difficult to do. Okay? So let me just begin and you will see what I mean by this. So first of all, as you all know, this is the Schrodinger equation that we need to solve. I h bar del psi del t. This, of course, is the actual Schrodinger equation. H psi equal to E psi is a consequence of this. And frankly, because of the fact that most of our courses spend most of the time trying to solve H psi equal to E psi, people tend to forget that H psi equal to E psi is nothing but a separation of variables step in the way of actually solving the time-dependent Schrodinger equation, which is the actual Schrodinger equation. The time-independent Schrodinger equation is just a consequence. Anyway, the point is, in physics, the aim always is to find out about time evolution, how things evolve in time. And that's exactly what the Schrodinger equation, this one, actually does for us. Okay? And as was already mentioned, unit choice is very important. Actually, the real problem is H cross M, these are tiny numbers in physical units, not physical units, in normal units. And they are very bad things to put in a computer. If you put in very tiny numbers alongside very large numbers, there's always a chance of round of errors becoming very huge. So although you can actually put in SI values of H cross and M and do the calculation, it's never advisable. In every numerical calculation, the best thing to do would be to choose your system of units in such a way that your numerical quantities that appear in the equation are sort of the order of 1. All of them are roughly of the same order. If that happens, then your equation sort of can be handled stably. That's a standard rule in all of numerical computation. You should not have huge numbers and very, very large numbers and very small numbers in your calculation. And usually if these involve dimensional objects, then if you have very large numbers or very small numbers, it simply means that you're using bad units. Of course, we are used to using SI units, but SI units are simply not designed for the microscopic world. They're designed for macroscopic world. So in the microscopic world, of course, you would use better units. You could use better units. That is a philosophical statement usually, but if you're doing numerical computation, then no longer is a philosophical statement, then it's actually a matter of being able to get the thing to work and not getting the thing to work. Nowadays, of course, with double precision computers and so on, things have become better. You can handle very small numbers and so on, or astronomically large numbers. But still, it's never a good idea to have in a given algorithm things of different scales. So what we are doing is we are choosing our special units, and the units we choose essentially make m equals 1, h cross equals 1. And there are dots here which sort of indicate that if there are certain special parameters in the V, for example, if V is a harmonic oscillator, half m omega square x square, then in addition to m being 1, I will also put omega equals 1. So I will try to get rid of all these dimensional parameters as much as possible by choosing units properly. And then going back to the actual, if you want to go back to the actual units, it's a matter of simply changing the scale. And that's a very standard, in fact, that's one of the standard things we should teach all our students to do, even by inspection. But anyway, this is the equation that we need to solve. This, of course, is a partial differential equation. First order in time, second order in space. Essentially the same kind of equation as the heat equation, which is also first order in time, second order in space. And apart from the I, which is what Abhijit referred to, apart from this apparently troubling thing that you have, this square root of -1, this is actually the same equation as the heat equation. And it belongs to a special class of partial differential equations called parabolic equations. And so it's really more like the heat equation than the wave equation, which is of a different class than our traditional wave equation. Although the presence of I essentially makes it behave unlike the, so basically what happens is in the diffusion equation of an exponential decay term because of del t, because of the I, you have it is the I omega theta. So that makes it like a wave. Anyway, that's something we are going to anyway get out of the solution. So of course, special cases, V of x can be chosen to be half x square, as I said. Instead of m omega square x square, I will just rescale my units in such a way that this becomes half x square. Of course, 0, free particle, V0 theta x minus x0, this is step potential. These are some examples of potentials that you can deal with. Now, because we are not going to use state-of-the-art or very advanced techniques for solving these partial differential equations, simply because they will take way too much effort for the student to learn. By the way, I hope I'm still connected. That's one problem it's presenting. I can't really see the screen.
Yes, you are.
Yes, you are.
So it will be nice if from time to time somebody responded. That is, I keep on feeling very jittery as to whether I'm still talking to a empty screen or not. Anyway, what we will see is because we are not going to do the high-end, use the high-end algorithms, there will be some shortcomings of these programs. And so you will have to be aware of those shortcomings so that you can explain to your students, for example, when they see something strange happen, why is it happening? Okay. But let me just go ahead at the timing. Let's press on ahead without worrying about those problems. Let's try to sort of see in a simple-minded manner how I would go about and solve this. And the basic hint here is that we would use discretized version of space and time, not continuum, but essentially put space-time on a lattice, so to speak, instead of saying that x is continuous and t is continuous, which of course, as far as we know, they really are. We are going to break up space. For the time we are going to talk of only one-dimensional problems, simply because again, it's difficult enough to solve the 1D Schrodinger equation. 1D meaning one spatial dimension. So what I'm going to do is break up space into discrete points. So x0, x0 plus delta x, x0 plus 2 delta x, x0 plus 3 delta x, and so on. And time also, we are not, of course, going to take a look at all possible times. We are going to choose a time step delta t. And from t0, we will go to t0 plus delta t, t0 plus 2 delta t, plus t0 plus 3 delta t, and so on. So this is the first thing that we will do. We will discretize space-time. That is, as far as our work is concerned, we will just look at the wave function as certain discrete x's and discrete t's. So x is x0 plus k times delta x, where k goes from 1, 0, 1, 2, 3, 4, and so on. This is xk. Sorry, I should have. And tn is t0 plus n delta t. Okay. So n here essentially talks about the nth time step. K here talks about the kth position on your spatial lattice. So basically what you're doing is you are saying this was your x, but now you have broken it up into a lattice of points like this. And as time goes by, you are trying to figure out what happens to the wave functions which were here, 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 here. I know what they were at the initial value. So this is the initial value problem in a sense. You know the initial value of the wave function. Then you want to find out what happens at the next time step. Then using that, you will try to find out what happens at the very next time step, and so on. So next, of course, this is something very trivial, which is because we are dealing with things only on a lattice, what we need to do is approximate the del psi del t and del 2 psi del x2. Which are sitting in the differential equation there. So del psi del t at xk and tn obviously is limit as delta t goes to 0 of this quantity. You keep xk the same, change tn to tn plus delta t, find out how much psi increases, divide by delta t, and that then take the limit as delta t goes to 0. This is, of course, exactly what the derivative is, partial derivative is. This is the definition of the partial derivative. But on the lattice, we are only dealing with discrete space-time points. So what we are going to do is we are going to use what is called the finite difference approximation. Again, something which all of you are definitely well aware of is you're saying that you can go from Tn to an arbitrarily close point in time delta t. You say, okay, let's go from Tn to the next time step, Tn plus 1. And find out how much psi has increased and divide by the time step. And that, of course, is the average value of the partial derivative with respect to t in that interval. What we are going to do is we are going to approximate that average use the average value as the actual value of del psi del t. And the whole idea is if delta t is small enough, this approximation should not really bother us. Okay? Is that clear? And then what we do is we just change this. Yeah, the only reason why I asked is that clear is, I know it's clear. I just wanted to be sure that I'm still connected. Okay. Okay. So this is psi k n plus 1 in my notation. Just the notation is simply I'm going to label the k index as a suffix and the n index as a superfix. So this is just notation. There's nothing special about this. I just want to keep this spatial discrete label and the time label separate. The time is up here. The space label is below. No reason except that it's convenient to keep them separate so that you can see exactly what we are doing. So this is, of course, del psi del t, psi k, both psi k's, but one at n plus 1, one at n, and you divide by delta t. Of course, there's something which you have all done before. So we also need del psi del x. Actually, I need del 2 psi del x2, but del psi del x is, of course, the same thing, except that n is the same, k increases by 1, and you divide by delta x. And what you really need is del 2 psi del x2. xktn at xktn is, okay, this is again a standard formula for the second derivative. This is the simplest formula that you have for the numerical value for the second derivative. Not the most accurate formula, but the lowest order formula that you have, which is you take the value of the psi at the left, on the left, value of psi at the right, subtract twice the value of psi in the middle, and divide that by delta x square. This of course should be familiar to all of you. So the only thing perhaps unfamiliar would be the notation. That is, instead of saying at x plus h, at x minus h, I'm just saying k plus 1, k minus 1. That's it. So if there are any questions, please ask. I can't see the chat, so it's better if you unmute and ask. Now, this much was trivial. So what I do is I simply plug this in. This is our wave equation. Del psi del t is I by 2 del 2 psi del x2 minus I times vx. Okay, I had a minus IH cross on this side, and I had a minus sign here. I just move the I to the other side. That's it. So I am writing this as if psi has a derivative, and the derivative is equal to this expression on the right. And then I just plug in the del psi del t approximation and del 2 psi del x2 approximation. So this equation, while it looks a lot more complicated than the one on top, is actually just this one in the finite difference approximation. Del psi del t is just this thing, psi at k, because its partial derivative is to x, same k value, n has increased by 1, I by 2, psi k n plus 1, psi n k plus 1 minus 2 psi n k plus psi n k minus 1 by delta x square, minus I vx psi k n. Okay, you might very well wonder, can we do something better? Can we use, instead of using forward difference for the time derivative, can we use central difference? Or can we use some of the higher order technique like Runge-Kutta? We can. It's just that things are going to be difficult enough as it is. And the major difference, if you really think about it, between what you are trying to do here and say solving an ordinary differential equation is simply that this is really like a huge number of ordinary differential equations. So if you have discretized your lattice into n points, so your lattice, remember, has been broken up into points which were labeled 0, 1, 2, and so on. So if you have n points, you have your final label is n minus 1. So 0 to capital N minus 1, capital N, of course, not small n. Small n is for my time step. This many points, this many, so you basically what you are talking about is psi k n is, you can think of that as trying to solve one single ODE for each one of the small k values, that is for each one of the capital N small k values. And for any reasonably good approximation, you really need to have a rather tight lattice, which means you need to solve a lot of differential equations at once. So you can think of doing it like you're doing RK4, but then it will be 1000. Say if capital N is 1000, that is, you have discretized your spatial interval into 1000 points, then this would really be 1000 coupled first order equations which are solving by RK4. You can do it, and given the fact that modern computers are powerful enough, they would actually handle it. But frankly, there's not much to be gained by that, and we'll see why. Of course, if you really wanted very high precision, you would do it. You would do something like that. But there are other pitfalls which are more important. For example, the second derivative formula. Instead of using this one, we would typically use a second derivative formula which is more accurate than this one. Okay, something which is like something called the 5-point stencil formula or the 7-point stencil formula or whatever. And here you just have this minus IV times psi. Psi, of course, is psi at xk and tn, the psi kn. And in principle, if I wanted my v to depend also on time, as far as numerics is concerned, there's hardly much of a problem. You just change the vk to vkn, and that's it. Okay. Okay, now I must apologize for a lot of noise that will creep in here right now, because my kitchen is now occupied and I have an open kitchen, so you will hear a lot of noise. Unfortunately, can't be helped. Okay, any questions?
Not yet.
Okay. Okay, so this is, now all you do is move this delta t to the other side and you're done. Essentially, you've got a, what do you need? You needed you knew psi k0. You knew psi k0 for all the k. That was the initial value given. So the basic problem is you know an initial wave function and you want to find out how the system evolves in time. So that is the problem you're trying to solve here. So you know psi k 0, this will give you psi k 1, then you repeat it again. Remember, this expression, everything in this expression apart from this one term will depend on psi k 0. So if you know all the psi k zeros for all the k's, then you know how to calculate this side explicitly, and then you can find out psi k n plus 1, psi k 1 from there. Then once you found out all the psi k 1s, you can use it to find out all the psi k 2s. Then you can use it to find all the psi k 3s and so on. So in principle, it seems that things are pretty straightforward. Okay. And this, if you just rewrite this a bit, move the delta t, as I said, move the delta t to that side and move the psi k n to the other side, you've got an explicit formula for calculating psi k n plus 1 for the time evolution. Psi k n plus 1 is simply psi k n plus this big combination I delta t by 2 delta x whole square minus I v k n delta t psi k n. That's it. Okay. So in principle, the problem has been solved. There's nothing much to do after this. Okay. In practice, it's quite a different story. That is precisely, otherwise I could have just said, give me 15 minutes, I will tell you what to do. In fact, I didn't even have to tell you what to do here. It's just absolutely trivial. Okay, let me just since in anticipation of the fact that it's going to be more complicated soon, and it has to be more complicated, let me just rewrite this a bit. I'm going to call this parameter I delta t by twice delta x whole square, which is going to come in over and over again. Let's call that mu. Okay. And if I do that, then I can easily see that psi k n plus 1 simply becomes mu times psi k plus 1 n, this one, plus mu times psi n k minus 1, that's this term. And if you couple all the other terms together, which all depend on psi k n, I plug them all in, I get this expression. Okay. So now there's one problem here. Remember, my k runs from. Okay, I should have some space. Okay, this is going to be nasty, but I'm going to write here anyway. Let's use some other color, black. My k values. Oh, I forgot to change the color. My k values run from 0, 1, 2 to n minus 1. Right? If I have n points, I'm deliberately starting counting at 0, both because it makes my formula for xk simpler, also because I'm going to use Python. We all are. And in Python, indices starting from 0 are what you use. And if you notice, for each of the k values, I can actually use this equation, except for the 2 points at the two ends. Right? Because for k equal to 0, if I try to using this equation, I would need psi n minus 1, which I can't figure out, right? I don't know what psi n minus 1 is. There is no minus 1 here. Similarly, for k equal to n minus 1, which is the largest possible k, if I try to write the equation simply like this, I will need, for this term, I will need psi small n capital N. There is no capital N in my index. And if I really just did it blindly, I will get an out of range index error in the NumPy. Okay. But more importantly, those terms don't exist. So basically, in all such problems, the boundary is important. At the extreme points, the equations change. So handling those extreme points become a bit of a problem. Or, well, it's part of your algorithm. How would you handle the two extreme points? So the important thing that is really an issue here is that we are not really solving just an initial value problem. We are also solving an initial boundary value problem, in the sense that the initial value for the wave function is given, but I also have to be sure what the boundary, what is happening at the edges of my spatial extent. Okay, and this is, of course, this is nothing only because of the math. This is not only because of the mathematics or the computation. This is very physical. In fact, if you think of the heat equation, which is the same kind of equation as I said, the most common situation where you solve the heat equation is essentially you are given a temperature distribution on a rod, but you're also told what happens at the two ends. Maybe one end is held at 0 degrees Celsius, other end is held at 100 degrees Celsius. Or maybe the other end is being heated and cooled at regular intervals. Okay? Maybe those are things which might very well be done. Okay? So basically what is happening at the boundaries is important, but since this is complicated enough as it stands, I'm going to simplify the problem by assuming the wave function vanishes at the boundary. So, which is, of course, if I really had an infinitely long straight line to play with, that would be perhaps perfectly physical. All we are going to do is we are going to assume that my wave functions are confined to vanish at two ends of a rather large line segment. So essentially, I'm putting the whole thing in a box, so to speak. This is not essential. You can actually go beyond this, but that takes a lot of effort. Okay, and as long as you stay confined to well within the box, the fact that there are boundary walls should not matter. But as I say, because we are using simple-minded algorithms here, boundaries will cause a problem. And as teachers, you have to be aware of those, because when your student comes to you and says, okay, this code is showing some crazy kind wave-like baby behavior, which I don't know can happen, which the exact solution doesn't tell can happen, you would have to realize that that's happening perhaps because of this one problem, that because you're not actually solving say when you're solving a free particle, we are trying to solve a free particle by putting Vx equal to 0, for example. If we just drop this V, it would be a free particle. But we are not really solving a free particle. We are solving a particle in a rather large infinite well. So the boundaries will make a difference. But in the long run, in the short run, it won't. So frankly, you can extract most of the physical information from this, except that things are going to become a bit problematic. So this is something you have to be aware of. Because of the limitations of because we are trying to keep things simple, and we are just insisting, for example, what we are trying to say is psi 0 for all n is 0, and psi n minus 1 for all n is 0. So that's the boundary condition I'm going to use. So I'm not even going to try to update their values. The values will be updated only for k equal to 1, 2 up to n minus 2. Updation will not occur for psi 0 n and psi n minus 1 n. They will be kept at 0. And because they will be kept at 0, using this equation doesn't really matter, because this will just give a 0 expression. Say for psi n 0, when you're trying to work it out, because they will be held at 0, if you try to write down psi 1 n plus 1, there this term is not there, but this is multiplied by 0 anyway, so it doesn't matter. So I hope this part is clear. I'm deliberately sabotaging the problem a bit just to make it simple enough so that we can handle it at this level. You can, of course, do better. You can incorporate actual boundary conditions or try to figure out how to handle infinitely long segments and so on. But those are much bigger complications than are warranted at this level. As you will soon see, even this apparently simple thing is not really so simple. So what I wrote down right after this is boundaries complicate matters. We will avoid this by setting dead wall boundary conditions. These are exactly the dead wall boundary conditions. So updating will happen only for, I will try to find out psi n plus 1, 1, psi n plus 1, 2, up to psi n plus 1, n minus 2 from here. You have endpoints, the two endpoints are fixed. You will only update the middle part. Okay, and what we will do is we will just for the, you don't really need to do the next part that I'm doing here for the computing. In fact, this updating routine can be very easily written down using NumPy slices, as we will soon try to show. But because of what comes next, what I thought would be good is if I could just write this down as a matrix equation for these vectors. So it should be pretty easy to figure out that this is what those equations really look like. Psi 1 n plus 1 is 1 minus 2 mu minus I del t v1 at n, potential value at x1, times psi 1 n plus mu times psi 2 n plus nothing. So here, one thing is this is highly local. That is, the derivative or the updating that we are doing for psi kn, that depends only on k plus 1, k minus 1, and k. Right? And that means that when you write down a matrix for this, the matrix will be a nice tridiagonal matrix. There will be terms down the diagonal, which are exactly these terms. 1 minus 2 mu minus I delta TV Kn. These will be sitting down the diagonal. Well, 1 minus 2 mu is a fixed quantity, and if you have a potential, of course, the potential can change from x to x. So at different points, it will have different values. So this is there's still a diagonal term, and the off-diagonal terms are fixed. They are mu on both sides. Okay. So basically, what you can think of is you can think of putting all these psi's for k equal to 1 to up to n minus 2, the ones you are going to update. You can think of putting them all in a column vector, and then this matrix, this n minus 2 by n minus 2 matrix, which is acting on it to give you the next value. Okay, so this is the straightforward thing that we can do. So we can use a Python. By the way, this is a tridiagonal matrix, which means most of its elements are 0. Only the diagonal term is non-zero. The leading subdiagonal and the two leading subdiagonals on the both sides, and superdiagonal on the both sides are non-zero. Everything else is 0. So this is a very simple structure. And because it has a very simple structure, there are special algorithms which can help you to calculate the things much more easily. We are not going to go into that once again because we are not going to go into special algorithms. We are going to treat this as any ordinary matrix, and we will use a standard NumPy matrix handling things. But you should be aware that because these are sparse matrices, especially because these are tridiagonal matrices, which are very special kind of sparse matrices, handling these equations numerically, if you really wanted to push it beyond the simple kind of applications we are doing, is actually quite possible. And tridiagonal matrices, there are special routines for handling them. We are not going to go into that right now. But are there any questions about this so far? Because I will now go into start showing you the implementation. If you have any confusions about this. Okay. If you don't have any confusion, please tell me, because I need to know that I'm still here.
No, it's okay, it seems.
Okay. Okay, fine. So this looks pretty straightforward. And as I said, nobody really would use matrix multiplication to do this updating, because this is trivially doable just by using slices. And I would urge you all to think of how to write down one line. In NumPy, it's one line of code, just one line or maybe 2 lines at most, to use a slice to do the updating. But because we are going to need matrix multiplication soon for the next methods that we are going to talk about, let me just show you the code using the matrix multiplication.
Abhijitda has a question.
Yeah, go ahead. You have to speak.
You are solving this complex matrix altogether, right?
Yeah, okay. That's a one point which Abhijitda made, which I should have addressed. He talked about changing the real part and imaginary part and so on. Frankly, Python and NumPy is clever enough to handle complex numbers wonderfully well. No need to treat that any differently. Just you have to put in the I in the right places. Okay. So I will not, if you are using most programming languages, you might have to separate this out into a real part and an imaginary part and solve them separately, which is of course nothing wrong about that. It's just that you don't need to do it when you're using Python. Complex matrices are perfectly well handled by NumPy. Okay. So I hope I made that clear. And the only thing that made me, that's irritating to me about this I here, as far as this discussion is concerned, is that I used I earlier for the spatial index, only to realize after writing a lot of it that I had to use I for square root of -1. I could have behaved like a in electrical engineer or somebody who's doing doing electronics and change I to J. But I didn't decide to do that, so I changed all the i's to k. That took me some time. All these spatial indices to k, because I had to use I for square root of -1. Other than that, complex numbers, no problem. And in NumPy, no problem. And okay, I'm not as brave as Abhijitda is, so I will not try to write down the program in front of you. I make immense number of errors when I try to type out a program. And this is complicated enough not to try it. I usually try demonstrating things like this to my class, only simpler programs, and even then I sort of mess up. So I just have a program which I've already written. It's a straightforward program. This one I could have perhaps written on the fly, but let me just show you what the program is. So what I have is import numpy as np, import matplotlib.pyplot as plt. So I'm going to use matplotlib to plot this. Full screen করলে কি ভালো হবে বেশি? মানে এটা বড় ফন্ট লাগবে?
না 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 না, লাইনগুলো ক্রস করে গেলে দেখতে পাবো। ঠিক আছে, ওকে ওকে ওকে।
না, কারণ ব্যাপারটা হচ্ছে ফুল স্ক্রিন গুলো তলায় চলে গেলে কিছু জিনিস স্ক্রিনের তলায় চলে যাবে।
আচ্ছা আচ্ছা, না 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 না, ঠিক আছে ঠিক আছে, at your convenience.
I think this should be, I hope this is visible. If not, I can increase the font size, but I think this should be okay.
Okay, 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 okay.
It's okay.
So basically, okay, this is pretty straightforward. I've imported numpy as np simply because I don't want to keep on typing numpy all the time. I definitely don't want to keep on typing matplotlib.pyplot dot something, so I imported that as plt. So this is for the plotting graph part. I've taken my straight line, which should really be from -infinity to +infinity. I'm really just discussing a free particle now to begin with. So v is 0 in this program. I've just done it from -10 to +10. So L is 20. That's the length of my entire line segment. So I'm going to go from -L/2 to +L/2, and I've chosen n, capital N, the number of steps, to be 1000. Okay, so this is my lattice discretization, 1000 spatial points. And then, okay, this a, x0 and k, these are nothing but just values for defining my wave function. Okay, I should have perhaps written down the wave function for you, but I think you can all make out what the wave function is going to be. So the first thing is I want this discrete lattice, which I do by just using linspace command in NumPy. Straightforward, nothing special, just using the linspace command to get a lattice from -L/2 to +L/2, 1000 points. And I'm using the rest step equal to true argument, which says that not only does it give me the array, which is the array of x's, it also gives me the step size, which it does in a tuple, and I've unpacked that into two values. The first value is the array, the second value, h, is the step size. So delta x is h in this program. I could have written dx, but anyway, I think that would be, h is fine, I guess. And then what I've done is I've used NumPy's universal functions to essentially define a Gaussian function for us. Right? You can easily see what has happened. I've just taken all the x values and I've just created a new array of psi values, which I'm calling u's. Psi is u for me here. So u's. So this was all the x's from -L/2 to +L/2 in 1000 points, and this is all the psi's. np.exp minus x minus x0 whole square by a square. Okay, so a square, maybe just put in a, doesn't matter. And okay, so this is the complex number. I put in 1.j, that's the complex number I. I hope everybody knows this, right? That the way to represent a complex number in Python is real part plus imaginary part followed by j. And this is the j, of course, which is what every engineer uses for square root of -1. So this is I kx. So basically what I've done is I've just taken an unnormalized wave function. I could have normalized this. Frankly, it doesn't matter too much. I could have divided by the normalization factor. But this is just a Gaussian which is centered at x0 and has a momentum term. It is the ikx term, which means it's moving towards, for a positive k, it's moving to the right. And then I've taken a dt, which is very, very tiny, 0.00005. And then I've gone and defined mu, which is delta t by delta x whole square, that's delta t by h square, into I by 2. I delta t by 2 delta x square. That's it. Now the best way of writing this, maybe I should have clubbed them properly. But anyway, this is I delta t by delta x square by 2. Okay. So there's just mu, the mu that I'm using here. And then I say, okay, we start at t equal to 0, we will stop at tf equal to 10. And then what I'm doing is 4 lines which essentially just plot the graph for us. So plt.plot, which plots x, and of course, what do I plot? My psi is complex, so I could have chosen to plot the real part and imaginary part. I just kept things more physical. I plotted the absolute value squared, that is basically mod psi mod square. And we want to see what happens to psi mod square as it evolves in time. And these are just the vertical axis and the horizontal axis. Okay, these 2 lines just plot the vertical and horizontal axis. And this sets the limits, the y limit, so that it doesn't auto scale and doesn't blow up. Okay. So y scale is being drawn from, in fact, it should be drawn from 0, but just because I want to see the, right, because I'm plotting y psi square, so psi mod square, so that's always positive. What I'm deliberately doing is starting from minus 0.5 just so that I can see the axis properly, and going up to plus 1.1. These are just ways of making the graph look a bit better. The only thing which is important here is this one thing. Is this something which is obvious to everybody, or does this need an explanation? Yes?
Please explain, sir.
Okay, so basically, if you use matplotlib.pyplot, so let me just see. Let me just try importing matplotlib.pyplot here. As PLT, and let's say I have a very simple thing to do. X is equal to np.linspace so that's an array of from 0 to pi of 50 points. 50 is the default value for the number of points for linspace. And let's say y is equal to np.sign xs. So this is a simple thing that you do when you want to plot a graph using matplotlib. But if I now do plt.plot x's comma y's, I will draw your attention to what it actually returns. The good thing about using the interpreter is that you can get to see what it returns right in front of you. Okay, so what kind of object is it returning? What is this? Can anybody tell me that? Say if I stored this somewhere and then asked for its type, what will the type be?
Tuple?
No, it's not a tuple. You can see what its type is just by looking at what at the screen. In fact, if I just write the type of the last output, that's underscore, it tells you what this is, right? It tells you it's list. And it is a list, it's in a square bracket, right? Anything which you have in a square bracket in Python is a list. This is a list. Now, why is this a list? That is, what it really returns is something. This thing within angular brackets is a so-called 2D line object which matplotlib uses to store various informations about the graph it's going to draw. Okay, that's the thing in the angular brackets. That's the entry of your list. The question is, why do you at all return a list? And the answer is because you could actually plot perhaps So plotting this, you could have plotted something like this. That is two graphs, right? Two graphs using the same plot command. This one returns y versus x versus sine x. This one returns x versus sine squared x. So there are two graphs, and note, now you have a list with two objects. As simple as that. Okay, clear? So that's what matplotlib always does. If you're just using plt.plot, it creates those two objects. You're not storing it somewhere. I'm actually storing it here for a special purpose. I want to update this graph as time progresses. That is, as I keep on calculating more and more terms, I want to keep on updating the graph. Okay, that is why I need access to the line object. To this object, which is a 2D line object, which matplotlib produces. It produces two line objects here. If you're plotting only a single graph, it would produce one single line object. Okay. So what I'm doing is simply, when I write line comma equal to, this comma is a sign that you are going to unpack whatever is on this side into multiple variables. Here I've given only one variable. So the list gets unpacked. The first entry of the list, the only entry of the list, goes and gets stored into line. By the way, I could have just done the same thing here, simply by doing this. This may be more familiar to most of you. Okay? Right? Because I'm just taking the 0th element, which is the first element of the list. The important thing is what plt.plot gives you is a list, and I don't want to save the list. I want to save what is in the list. That's what I did a while ago. Is that okay? Now, why I want to save the list, you will soon see. But before you go there, let's come to this. So as I said, you don't need a matrix. You can just use slicing to do this. But I will just use a matrix anyway. Okay, so the matrix, what kind of matrix is this? Let me just go back to the matrix and show you. And for the timing, just forget about the V. This is the free particle that we are talking about. So this minus I delta t V terms, these are not there. So all the diagonal elements are 1 minus 2 mu. Very simple. The first leading subdiagonal is all mu. And on the other side also all mu. Right? Okay. So there's a very nice way of creating such arrays. Not really matrices, but two-dimensional arrays look like matrices to us. And we are going to treat them as matrices. So basically what I need is an identity matrix times 1 minus 2 mu plus mu times a shifted identity matrix plus mu times identity matrix shifted the other way. Shifted meaning shifted off diagonal. So I'm not sure everybody here knows this command in NumPy, but NumPy has a command called np.I. By the way, EYE, that's meant to be pronounced I. It's a pronunciation which is being looked at here, not the word. It doesn't mean what you see with. It's just I for identity. So this produces an identity matrix. Okay. Say 30 would produce a 30 by 30 identity matrix. Okay, maybe a bit too ambitious to maybe 10. You will see a 10 by 10 identity matrix. Okay. But the good thing about I is that it actually can give you something else. You can actually specify shifted identity matrices. That is, when you say k equal 2, notice that the leading diagonal is still 0. What has happened is that the ones have shifted to the second sub-major diagonal. That is, shifted two places to the right. And this shifts it 2 places in the other direction. So the major diagonal is 0, the first subleading diagonal is 0, the next subleading diagonal is 1. Okay? So this essentially makes it very easy for us to create this matrix. 1 minus 2 mu along the diagonal, mu along the one above, mu along the one below. So that's in our program that simply translates to n. Okay, what is the dimensionality of this matrix? It has to be n minus 2 dimensional. Remember, because only the middle n minus 2, not the 0th, not the last, but only the middle n minus 2 is being changed. Only those are being updated. Only the Kishore, are you here?
Yes.
I was told that somehow on the YouTube live, it seems that other voices like yours is coming all the time. Maybe that's because of something else you're using to use the YouTube recording. And I can't hear that.
Yeah, actually,
I'm using the YouTube live. She informed me that maybe there's some noise coming in because of that.
Okay, I'm checking.
But I can't hear it.
On YouTube live, you can't hear anything. So you're on Google Meet, right? You are talking to me on Google Meet.
Yes, but when I hear it over the phone, my mobile phone, I'm hearing it okay. No other sound.
Maybe বাড়িতে তোমার feedback হচ্ছে আনন্দ?
Oh, most likely what is happening is my own voice is coming back.
Okay.
বাড়িতে problem টা হচ্ছে।
I can hear Kishore than more.
Okay. Anyway, I hope that can be sort of that. It shouldn't be too much of a problem. But okay, let me just point out that you have an n minus 2 by n minus 2 matrix here, right? Because we are not changing the last and the first point, just the n minus 2 points in between. So I need an n minus 2 dimensional identity matrix, multiplying that by 1 minus 2 mu, right? That's what you needed. Then you take n minus 2 dimensional identity matrix with k equal to 1, which means shifted up once, multiply that by mu, and the same thing with k equal to minus 1, multiply that by mu, that gives me this matrix. Clear? Is that clear to everybody? This is simply how you produce this matrix.
Yeah.
Once again, this is completely unnecessary in the sense that you don't need to use matrices here at all. And maybe using matrices is a bad thing because it makes the program slower. But slicing is faster. But anyway, we will need matrices soon. So what we will do? What we will do is simple. This is all you are doing. While t is less than tf, you're going to update the use, but not the whole use, just the slice of use, leaving out the 0th term and the minus 1th term. Of course, I hope everybody remembers that much of numpy, that when you slice it like this, it means the 0th term is out, the minus 1th term is out. Only the middle part, you are replacing that by just multiplying the matrix A by US 1 colon minus 1. I'm not using the matrix matrix object in numpy because that's actually slower. I'm just using the dot which numpy gives you, which essentially carries out matrix multiplication. You can't just say A star US 1 colon minus 1 because that will do something entirely different. The dot is exactly what does matrix multiplication for us. So this is just matrix A, or this matrix which I called M here, times the psi bar, where psi bar is this column vector with all entries of the psi except for the 0th one and the n minus 1th one, the two extreme ones. Okay. And I'm changing the t to t plus equal to dt. That's it. Okay. So I'm just updating the u, updating the t, and the only new thing that I've done is this. Only thing which is a bit non-trivial. And this is why I actually stored this thing in line. Okay. This line is a 2D graph object. It has all kinds of things inside, like what are the x values, what are the y values, what color, what marker to use. Every information is inside that object. And like all objects, it has things which you can use to change it. Here, there's a set y data function, which the line object has. And all I'm doing is, now that I've calculated is a new value of shy, I'm going to just change the y data that was used in the original graph. I'm going to set the y data to the new value of u. That's it. Okay, not the new value of u, but u mod square. Of course, because I'm using NumPy, this happens element by element. Every element in the array is mod squared, and you get a new array, and so on. And the only tricky thing about this is, if you forget to put in a plt.pause here, life is going to be very, very bad for you. Frankly, I've seen a lot of discussion about this in NumPy user groups and Matplotlib user groups. Nobody is sure why the plt.pause is needed here. plt.pause, of course, just pauses the drawing for this amount of time, that many seconds. Nobody knows why you need a plt.pause here, but it seems that if you don't put in the plt.pause here, the program simply will not work. As simple as that. Okay. With the plt.pause, it will work fine. Of course, if you put in a large time pause, it's going to take a long time to change. Okay. Any question? Okay, so let me just quickly show you the whole program again. Really rather simple. You imported NumPy, you imported Matplotlib. This part, if you want the graph, if you don't want the graph to show up and have a fancy wave function running on the screen, you don't need the Matplotlib. But anyway, this is easy enough. You decide how long your line segment is, how many points you want to break it up into. These are just parameters for the Gaussian wave function. That is, what's the width, what's the sigma, what's x0, what's k, the momentum. This is all the x values you need. You just created the corresponding wave function. This is the initial wave function. Now taken a pretty tiny time step, 0.00005, and then just evaluated mu using the h and dt, and then this is just the plotting line. This just produces that tridiagonal matrix for us. And there are other ways of producing the tridiagonal matrix. I just did it most explicitly. And then I'm simply updating. At every time step, I just update by applying this matrix. End of story. And this is just change this one, line.set underscore y data. Line is just the name of this variable, whatever object you have stored the graph in. And you're setting the y data every time, so which means every time a new y is calculated, it updates the graph. So we'll see a moving graph. Okay, that's how you produce animations in Matplotlib. As simple as that, nothing much more. The only tricky thing is, if you don't have the plt.pause for reasons which nobody seems to understand very well, the code doesn't really work. Okay. Any questions about the code at this stage? Because this is the kind of code which we are going to write to solve the problem. If there are no questions, I can merely go ahead and show you what the output to this program is. And yeah, is there a question?
I think no questions is there.
That's big. Okay, so let's run the program, and it's going to be very boring. Let me warn you about that. This is the output. And if I put my pointer right here, and if you wait for a long time, okay, you can see what's happening, right? Something is happening. I'm not moving the pointer. So very slowly, the Gaussian is shifting to the right. Okay?
Mm-hmm.
Why is it doing that so slowly? Why is it doing that so slowly? That should be a question which is very easy to answer.
T has been put very small value.
Yeah, not T, dt, right? Yeah, we have put in a horribly small value of dt. So I've just stopped the program. Okay, but let's see. Let me try to improve upon this a bit. It should be easy to... Oh, sorry. I ran the program again. Let me just edit the program. Just change d to a slightly larger value. Maybe just make it 10 times larger. 0.0005, still pretty tiny, right? Now notice what has happened. Okay, you have got an output which is completely crazy.
Y এর upper limit টা বাড়িয়ে দাও না ওই মাথাটা
কিছু হবে না প্রথমত you have just now got a overflow runtime overflow, which means it has gone beyond what the numbers that Python can handle, which is pretty huge numbers. Okay, the point is that this algorithm, this simple-minded algorithm, will only work if delta t is tiny. In fact, even the 0.0005 value that I used a while ago, the value which I used a while ago, is actually too big. Not this one. This one is too big, as you can see. Even this one, which was pretty bad to begin with, looked pretty slow and did nothing. You pay attention, you will see that not only is it shifting to the right as it should, something else is also happening which should never happen. You all know the physics of the
এটা তোমার ডিসক্রিটাইজেশনের জন্য হয়েছে আর কি, তুমি যেভাবে ডিসক্রিটাইজ করেছো সেখানে তোমার ডেল্টা টিটা এত কম নেওয়া ছাড়া উপায় নেই, তাই তো? মানে এইভাবে
কিন্তু বক্তব্যটা
একটা ফরওয়ার্ড ডিফারেন্স আরেকটা
না হচ্ছেটা কি এখানে যেটা হচ্ছে সেটা সাংঘাতিক, সেটা হচ্ছে the wave function is growing, right? You should never do that. You should actually drop off.
Normalize করতে হবে তোমাকে, তাই তো?
এখন বক্তব্য হচ্ছে যে সোজা there are two things here. One is this, what we are essentially doing is something like this. Now this is again something which the teachers here will of course appreciate. What should happen in actual time evolution, let me just get some space for myself here. What should happen is wave function at time t should be e to the minus t I t h hat. H cross is 1, so let's not worry too much about that. Psi at 0, right? This is an unitary evolution. This operator is unitary. It preserves the norm. What we have done here effectively is we have replaced this with 1 minus I delta t h hat. The first order approximation. That's what we have essentially done, right? But notice what happens when you do this. This thing is unitary only to first order. This thing is exactly unitary. This one is not. And because this is not unitary, it's not going to preserve norm. In fact, if we were to use this approximation, it's very easy to see that what is going to happen is right. So that's, if you just multiply it out, you will see that what comes out is 1 plus so after one time step, it grows by a factor which is 1 plus delta t square times the expression of the energy. And that means this is of course something which happens at every time step. So norm keeps on increasing with time. So this problem will not preserve norm. If you want to use it, you will have to keep on rescaling the norm every time. Not a good thing to do because that's a lot of computation. But you will have to do it. Without that, it will not work at all. But what is worse is what you saw for a slightly larger value of delta. This huge thing that you saw when delta t was 0.005 was not because of this factor. This factor is an irritant. It's going to increase the norm very rapidly, but not that rapidly. What you were saying here is something which is pretty straightforward. You are essentially applying the same matrix over and over again, right, on Cheyenne. Now, if you keep on applying the same matrix over and over again, a standard matrix theory that the largest eigenvalue of the matrix is going to dominate in the long run. And if the largest eigenvalue of the matrix has an eigenvalue which is more than 1, then in magnitude, then the system is going to simply keep on each iteration, the system keeps on blowing up and it becomes unstable. So it's not just a matter of rescaling or anything. Rescaling will not save you. This particular algorithm, very simple-minded, very easy, is not a good algorithm. For the simple reason that it's going to make the whole thing blow up. It's unstable. It just cannot give you a good solution. Unless mu is really tiny. Okay, that this very tiny value of delta t which I had to use, actually, basically the point is this delta t by delta x squared by 2, this magnitude has to be less than 1. Or actually less than half. I don't remember the exact limit right now. I can actually work it out pretty easily. This is a pretty straightforward calculation in standard matrix theory, finding out the eigenvalues of this tridiagonal matrix. Because this is a tridiagonal matrix, it's pretty easy to find out its determinant and its eigenvalues and so on. Elementary calculation. But once you do that, it will turn out that unless delta t by delta x whole square is smaller than a bound, it's going to blow up. It's going to be unstable. And that actually is dangerous because if you want to get any degree of accuracy, you have to make delta x very small. But notice the delta t has to go like delta x square. So if delta t becomes smaller, delta x becomes smaller, delta t has to be even smaller. Okay. So, of course, using a very tiny delta t is boring because it's going to make the program very slow. Much more dangerously because of the fact that when you use a very tiny delta t, you have to actually keep on doing it many, many times. And every time you do it, the norm increases by this factor. 1 becomes, what was 1 ends up becoming 1 plus delta t whole square times h every time. And because it's getting multiplied by the same factor which is bigger than 1. So this power of exponential growth keeps on blowing it up completely. Of course, you can normalize again every time. Bad idea because it's going to make the program very, very unwieldy. Okay? Right? Is everybody with me so far? This particular thing is what people call a fail in a social media language. This is a simple-minded algorithm which actually does not work unless you are prepared to use a very, very tiny delta t, renormalize at every step, and make the whole thing, make your life very difficult. Okay. But the only reason I brought this up was to show you that there are better methods. Okay, so Kishore, can I go on till say 15 more minutes after?
Sure.
Over?
Sure.
I will need some time, perhaps.
Please carry on.
So the explicit method, which is the straightforward method which gives you a new formula for finding psi kn plus 1 directly in terms of psi kn, does not work. So we go in for the implicit method, and there we are guided by two things. The theory of ODEs should tell us that instead of using the value of the derivative at the beginning, if you use the explicit method, the value of the derivative at the end, the algorithm ends up becoming more stable. So basically what you're doing is exactly what I did before. If you look at this expression, it should look exactly like what I had on a while ago. Okay, let me just go and repeat this. Show you what we had here. This is what we had. Psi kn plus 1 is psi kn plus mu into psi kn plus 1 k plus 1 n minus 2 psi kn plus psi kn k minus 1 n minus iv k n delta t, etc., etc. What we have here looks exactly like that. This is the first del psi del t approximation. This is the del 2 psi del t 2 approximation. This is the v times psi. So of course, all of you have spotted exactly what has changed, right? What has changed between that one and this one?
The last term is calculated at t plus delta t.
Yeah, the derivative, the right-hand side, which is the derivative of del psi del t, is being evaluated by using del 2 psi del x2 and v psi, of course numerically, but is being evaluated at t plus delta t at the end of the interval. The only problem with this, the advantage with this is more stable. Now I don't have the time to go through the whole mathematics as to why this is more stable. But it's very easy for you to verify that if you wrote this down in a matrix fashion and found out the eigenvalues, even the largest eigenvalue for any value of the constant mu is going to be less than 1 in magnitude. So this is unconditionally stable. So I just rewrite this, but rewrite this by just multiplying by delta t, pulling the psi k into the other side and so on. Straightforward. The only problem is here on the right hand side you have all the psi k n plus 1s, right? So this is not a formula for calculating psi k n plus 1 because psi k n plus 1s are there both on the left and on the right. So this is a set of equations which are to solve for psi k n plus 1s. Okay. So instead of the simple prescription that the explicit formula gave you, the previous one was an explicit form. This gives you psi k n plus 1, the psi k at the next time step implicitly. You have to solve for this, solve for the next time step psi k's. Okay. But it's pretty easy to do. It is using, that's why I brought in the matrices last time. Not needed, but I brought it in simply because I can pull every one of these terms to the right and then write this as some matrix m tilde acting on psi bar n plus 1. It's a very similar matrix than the previous one. The only thing that will happen is all the plus mu's become minus mu's and so on simply because they're moving from this side to that side. So m tilde psi bar n plus 1 is psi bar n and psi bar n plus 1 what acts is m tilde inverse psi bar n. Okay, clear? So I have to actually solve a set of simultaneous differential equations which this matrix is. Okay, this psi bar is simply the column vector. Remember again just the middle path, not the 0th and not the n minus 1th. And this is a set of equations I have to solve to get psi bar n plus 1, but these are simultaneous equations. Just invert the matrix, apply it, you're done. Not the most clever way of solving these equations because these happen to be tridiagonal set of equations, sparse equations, and there are many cleverer ways of solving this. So if you wanted to do bigger lattices and so on, you would usually use a cleverer way of solving this and not what I'm talking about here, not invert a matrix. Of course, because we are using NumPy handles large matrices pretty well. We can do it, but still not a great idea. If you really wanted, so as I said, we will keep things very simple for ourselves. That's why I'm just going to use matrix inversion here. So I will just rewrite this matrix, the same matrix as in the case before, except that I will change the sign. Okay, the mu's become minus 2 mu's and so on because they are just moved from the right hand side to the left hand side, and then use the inverse of that matrix. So in other words, instead of using one minus I delta t h hat psi 0, which was a approximation we were using before, what we are really using is this. Okay. By the way, neither is, so this does not give you unitarity either. So not a great idea that way in that sense, but still stable. It will not make the solution blow up. So how would you code that? So that was explicit. This is the implicit one. Same code, everything same, everything goes the same way. Nothing new, nothing new, nothing new, nothing new. This has changed. I've written the matrix A so that where in the original matrix A you had 1 minus 2 mu, now you have 1 plus 2 mu. Where you had plus mu times these shifted identities, now you have minus mu times shifted identities. And the only new thing that I put in is a potential. Remember, the potential is an additional term which goes down the diagonal, which is I delta t Vx, right? Times, that was the term which goes in the diagonal term. So that's what I put in. So what I've put in here is I, this is 1 dot j, this is just I, times dt by 2, I delta t by 2 because, not because of anything else, because of my potential is half x square. So I've taken all the x's at the, remember this is all the, not all the x's, is the x's barring the last and the first term. So that's why I've taken a slice of the x's from 1 to -1 and then squared that. That's the half x square potential. The 2 here is simply the 2 of the half x square potential. Okay. And then I've just used NumPy linear submodules inverse function, which inverts a matrix to get this. Again, yeah.
Sorry, could you do the free particle this way also?
Yeah. I would just drop this.
Was the potential necessary? No, they just read another example.
Just drop this extra term.
Okay.
I just wanted to show you what happens with the potential. And then you use B equal to NP dot V.
Okay.
Yeah. And then just you invert the A using the Linal's inversion. Again, not the cleverest thing to do, but straightforward, something which the students can do just by writing one line of code. And then the rest is just this. So I admit this looks a bit complicated if you look at the whole thing, but ultimately the code is really 3 lines. This line for creating the A matrix, this line for inverting the A, and then you have a loop which essentially multiplies B with the shies, the middle part of the shies, to update the middle part of the shies. That's it. And this, of course, resets the whole thing and so on. Now, I've deliberately chosen a much bigger value of dt here, 0.01, to make things faster. And this will be okay. Let me just start with this. So I'm starting with a Gaussian centered at the origin, and there's a harmonic oscillator potential. Let's see what happens. Okay, what is happening? So this is your time evolution of the wave function. So what's actually happening here? Yes? Well, what's happening here is come on, somebody can tell me what can you see on the screen? What's happening to the probability distribution? Well, the answer is simple. The answer is nothing is happening to the probability distribution. And it shouldn't happen. That's the whole point. The point is that actually is a good thing because it shows us that what I've done here is right. Why? Because the wave function I've chosen here, a wave function of just the right width, A equal to 2, centered at the origin, is exactly nothing but the ground state wave function for the harmonic oscillator. As a stationary state, as it evolves in time, nothing should happen to it. I guarantee you that if you started with this problem using the implicit method, it would have blown up in no time. This shows that at least the explicit method is, using the explicit method, the one we did earlier, even if you had started with this wave function with the harmonic oscillator potential, the thing would have simply blown up. Here, it doesn't happen. At least this one actually gives you the physically correct result that a stationary state does not change with time. Of course, that's not very interesting. So let's try to see what happens if we were to displace it a bit. So this is a displaced Gaussian, revolves in time. What should it do? Okay, it's oscillating back and forth, right? But this is also not very physical. Why is this not very physical? And this is stable, nothing is blowing up. But even this is not very physical. Okay, nothing is happening now because the program has ended. I just gave it 10 time units. But if I gave it more time, you would be able to see. Let's just. So notice at least that this is stable despite using a much larger value of delta t, nothing is blowing up. So that way is good. And a displaced Gaussian. Yeah. A displaced Gaussian is what is called a coherent state of a harmonic oscillator. If you take the ground state and just shift it, what you end up with is a coherent state. And it should oscillate back and forth in a harmonic oscillator potential. In all states in the harmonic oscillator should oscillate back and forth. But there's something unphysical happening here, which you can easily see, which is
Diffusion.
Isn't
it diffusing?
It's not diffusing actually. It looks like diffusing because its height is going. You mean its height is becoming smaller? Yeah, it looks like diffusing. It's not really diffusing. It's just losing its norm. Okay, why? Well, that's because if you look at this, this is also not unitary. But what it does is that it actually changes the norm of 1 to 1 by 1 plus delta t square exponential of h. So it basically makes the norm decrease instead of norm increasing. Okay. But at least here, with this method, which is slightly more involved than the previous method, at least nothing is blowing out, so nothing is unstable. By the way, the instability has nothing to do with Python, or instability has nothing to do with quantum mechanics. This is a standard problem whenever you try to numerically simulate a differential equation like this. And that's just pure maths. Nothing can help you out there. The instability is something you simply can't handle. This one can be handled by rescaling the normalization every time. At every step, if you rescale the normalization, at least you will get a decent, good behavior. Not perfect, but still good behavior. Okay? So now I will take so we have talked about two algorithms so far. The first one, the obvious one, very simple, very straightforward, does not work at all. Unless you are prepared to use horribly small delta t's, and in which case your norm simply grows like anything over time. Because every time you are taking a step, the norm is increasing. This one, stable at least, does not blow up, and can be rescued by renormalizing the wave function at every time step. At the end of every time step, you could calculate the norm, divide by the square root of the mod square integral using Sims or whatever other integration routine you want, and then this will be decent. But there is a better way of handling this which does not need any of this. Okay? And that's the third algorithm. That's my final algorithm for the day. There are many, many more. For those of you who have studied, say, Baker-Campbell-Hausdorff formula and so on, we all know there are many ways of handling time evolution in quantum mechanics using advanced operator algorithms. And those are not just things which you handle in, say, just in mathematical or analytical work. You also use them extensively in both symplectic algorithms for solving differential equations, also for solving the Schrodinger equation, as it depends on time. But those are more advanced algorithms. As I said, we'll just use the simplest possibilities. The simplest possibility is the simplest possibility which has two advantages, which is Okay, three advantages. It's stable. It's more accurate than either of the two methods I've talked about because it approximates the derivative to a higher order of error. To a higher order of error means, of course, higher power of delta t, which means smaller error. And it's also unitary. So it doesn't have this problem of the norm behaving badly. Okay. And that algorithm is the final one that I'm going to talk about. Is this the best algorithm you can have? The answer is no, but I think this is the best algorithm we can use at this level with students, which is the Crank-Nicholson method. And to understand the Crank-Nicholson method is really very easy. The two equations I've written down here are just the two equations that we have used so far. The explicit formula and the implicit formula. Okay. The explicit formula, everything is n on this side, which means if you know psi k n, you can find out psi k n plus 1. The implicit one, everything is n plus 1 on this side apart from the psi k n, which means you have to bring everything to this side. You get a bunch of simultaneous equations in psi k n plus 1, solve it. The Crank-Nicholson simply hinges on this idea. Instead of using the derivative at the beginning of the interval or the derivative at the end of the interval, wouldn't it be better if I actually use the derivative at the middle? That would be better. Or you could take the average of the two derivatives at the two ends, right? This is exactly what is done in, say, in what is called the modified Euler method. Okay, you take the derivative at the beginning, derivative at the end, average the two, and use that derivative. So that's all we are going to do. That's what Crank-Nicholson is. So psi k n plus 1 equal to psi k n plus this correction term. The two correction terms are different in the implicit and the explicit method. The implicit gives you this, explicit gives you this. Crank-Nicholson just averages the two. This is a simple-minded thing, but that immediately gives you several advantages. One of them is this is a much more accurate estimate of the del psi del t than taking the value at the beginning and the end. So the error is a lot less. And the other two other huge advantages, this is unconditionally stable for all values of mu. And it's explicitly unitary, because if you think about it, this is really what you're doing. So this is what Abhijit was talking about. This half essentially is like you are taking it forward for half the time step. There is delta, instead of delta t, you're using delta t by 2. That's why you have a half mu here. Okay. So you're taking it forward using the beginning interval, beginning of the thing, using half the time step, and using the explicit method for the other half. That is, what you're really doing is something like this. You're approximating the time evolution by this. So this is the operator which you're really using. You're using 1 minus I delta t h by 2 h hat to move forward, and then you're using the inverse of 1 plus I delta t by 2 h hat to move back from the end to the middle. Okay, but this is really, you're going forward to psi k n plus 1. This is just how you calculate the change. But can you see what is special about this operator? Now, if you're feeling uncomfortable of my writing one operator divided by another, just note that these two operators commute. So
yeah, if you take the dagger, then the numerator and denominator exchange. So the product,
yeah, right. So that means if you take the dagger, it becomes inverse.
The product becomes 1.
Yeah. So this is explicitly unitary. Okay. By the way, the Crank-Nicholson method is also extensively used for solving the heat equation in classical physics. Their unitarity is not a concern. There are the advantages: A, stability, and B, extra accuracy. But here, the advantage is stability, accuracy, unitarity, which is great. So with relatively small amount of effort, not a huge amount of effort, relatively small amount, you can actually overcome the difficulties that we had faced so far. So I must apologize for bringing you through the implicit, explicit, implicit, and here. But unless you saw those, you would not really realize why you want to use Crank-Nicolson. The explicit method, easiest of them to understand, easiest to state, horrible to use because of stability issues. The implicit method, no stability issues, less accurate, not unitary. So you either renormalize or simply get something unphysical like a wave function dying off its own. And Crank-Nicolson, essentially you still have, this is still an implicit method, of course, because you have psi k n plus 1 on both sides. So you have to solve this equation. So basically, like you had a m and m tilde, m with plus delta t and m tilde with delta t is changing sign, all the mu is changing sign, except that here you have m and m tilde for half delta t because of this extra factor of half which is sitting here. Okay, so same, you can rewrite the code that you wrote a while ago trivially, that I wrote a while ago. And the only difference is the matrix that you are going to use is actually m tilde inverse m, that's going to apply every time. Once again, matrix inversion is not the best way to do it, but it's good enough for this purpose. What I mean is there are easier ways, there are faster ways of solving tridiagonal matrix systems, which we are not going to go into. So, final algorithm. Okay, almost the same. I have just increased the length a bit, simply because I wanted to have more space to show various physical phenomena. I have several choices of potential written down. So, for example, it could be zeros, which is a free particle. This is the parabola, harmonic oscillator. And then I have a step in this line. Okay, not very important. 3 different potentials just for the x's defined. A Gaussian, as always. I just started with the Gaussian. I use a time step of 0.005. And now the mu is the same as always. I times dt by 2 delta x square. And what I've done, these lines are the same, but now I have 2 matrices, A1, A2, and B. Okay, and A1 is my matrix M tilde with all the, and remember you had 1 plus 2 mu in the M tilde for what you had in the M tilde for the implicit method. You had a 1 plus 2 mu here, you had a minus mu here, and a minus mu here. I just am replacing the mu by mu, half of that. So 1 plus mu, minus mu by 2, minus mu by 2, because the delta t by 2 thing. Okay. Similarly, for the diagonal, here I have explicitly written the v's. So I have already found the potential, so I don't have to multiply by half x square. So I just have I dt by 2. The by 2 is simply because we're doing it for half the time step. And A2 is just the same matrix as the one we use. So this is the same matrix as the one we use for the implicit method. This is the same one we use for the explicit method. The only difference is in the sign of the mu and the size of the prefactors. Those have been halved. And then I'm calculating the actual matrix, which I'm going to use to evolve, simply by using calculating the inverse, that's A1 inverse, and I'm multiplying that by A2. So I'm just getting A1 inverse A2 as my matrix B, which is the matrix sitting here, which is going to be applied on psi bar n to give me psi bar n plus 1. Okay. So done. Basically, if you go through the entire thing, it's really rather simple. All you're doing is L equal to 40, N equal to 10, some basic stuff, bookkeeping stuff, an array of x's, a potential defined at every x, a wave function defined. Now you step your dt and so on. And the actual calculation is just being done here. By putting this is the first 2 lines, the more complicated looking 2 lines is really just setting up the initial matrix. The only thing is that this is a diag. Okay, I've not explained what diag is, but I'm pretty sure all of you have guessed. Diag produces, if you give a 1-dimensional array, diag produces a diagonal matrix out of that. So it takes that 1-dimensional array and puts that on the diagonal. And that's all you need. That's the extra term that you need for the potential. And that's it. So let's see whether this works any better. So let's see, what do we have here? We have, what potential are we using? We are using the harmonic oscillator potential. Okay, let's see. And let's use k equal to 0 for the timing to begin with. Okay, so a equals 2 is just the width. X0 means it has been shifted to the left by 5 units. And let's see whether this works. Okay, so this is what the Gaussian wave packet will do under a parabolic potential. Okay, and the orange line is just the potential curve. Just showing you that you really do have a parabolic potential. And this is exactly what it means when you say this is a coherent state. It retains its shape perfectly. It just goes back and forth. Of course, the name coherent state came in not because of this coherence, but because it's in optics, it talks of optical coherence when you talk of similar states in optics. But basically, that's all this is going to happen. This is not going to die down. This is not exactly accurate, of course. But this is more accurate than either of the two methods before. It also has the advantage of no loss of norm. If you look very carefully, you might see the peak bob up and down a bit. That's the error that is happening because of numerical calculations. The exact solution here would just move back and forth without changing at all. That's what the coherent state does when it changes this way. Okay, maybe just to... So at least I hope everybody is convinced that this method at least gives you a much more accurate and reasonably distant answer for the time evolution problem compared to the previous two methods. So is this okay with everybody? So let me just see whether we can use this further.
Potential step.
Okay, let's just see what happens when a potential step. Of course, I can't comment out all the lines. Then, of course, I will not have any potential. Then the program is going to complain about not having any V's. Okay, this is straightforward, by the way. I hope everybody knows what where is. If you don't, it's just a simple utility function in NumPy which allows you to essentially ask this question. In the array XS, not the whole array, I'm taking the slice of the array which leaves out the beginning and the end term. Is XS negative? If the element negative, if it is, put in 0. If it's not negative, put in 2. So basically you ask a question. If the answer is yes, you put in the first answer. If the answer is no, you put in the second answer. Okay, so that's it. So this is basically an array which is 0 for x negative, 2 for x positive. So it's step. Okay, and of course I have to, now that I have a free particle, okay, let's start with this anyway. Let's see what comes out. Remember, there's no momentum of this free particle. So what it will do, by itself, it will just diffuse. That's what a free particle does, right? The step is here. It's looking hugely tall simply because my upper limit is 1. But now what you're seeing is the system is diffused. This is really the diffusion-like behavior. The Gaussian wave packet spreading, but not moving because there's no momentum. But now it has spread enough and it has just encounters the step. So you see reflection at the step. Okay. So here you see the effect of the step potential showing up. Okay, maybe as a bit more interesting would be So I put in a rather large value of the momentum in the positive direction. So it's moving to the right now. Now it encounters the step. Something happens to it, but not much. It keeps on going. And of course, it's a free particle on the left of the step, free particle on the right of the step, so it's spreading like a free particle should. But can anybody tell me why nothing? It apparently nothing happened at the step. Oh, by the way, this is what I was talking about. Do you realize what has happened here? Just now you saw something strange happening. And this is something which your students are going to bother you about if they
Reflection at the boundary.
Yeah, so you basically remember this is not really an infinite x. So it's reflecting off the boundary. And now something is happening at the step, but not very much. And again, when it goes and hits the other boundary at -20, it's again going to, that's an infinite boundary. You're getting reflections there.
তোমার তার মানে finite boundary হলেই তবে তুমি রিটার্ন করবে, otherwise it will not.
করবে না তো, otherwise if it's an infinite straight line it will
মানে
just
তার মানে এটা হচ্ছে যে দেখছো সেটা আর্টিফ্যাক্ট একটা আর কি।
The artifact, you can call it an artifact if you want to solve an infinite problem.
Yeah.
You want to solve a problem of particle in a box. This is exactly what a Gaussian
that is
wave function in a particle in a box.
But
does.
we are seeing only the step, effect of the step.
You are seeing almost no effect of the step. Yeah.
Almost, because k is high now.
Yeah, that's because the momentum that I've used is huge. So k square by 2, which is the kinetic energy,
Yes.
or which is the actual energy,
Yes.
is way more than the potential energy of the step. Okay. So what you saw earlier, you had k of 0, which means no total energy was 0. So the particle simply couldn't go through the step. Here, okay, so let's use a slightly smaller value of k. So here you will have a particle moving to the right, not slowly than before, of course. Okay, sorry. So it's going to move a lot slowly. But because k is smaller now, so the particle should not really penetrate the step. Notice what's going to happen.
There should be some reflection part from this wall.
Yeah, there will be reflection.
Step wall. Yeah.
So basically, this is really what, okay, when we actually talk about quantum mechanics problems, we usually talk about the stationary state approximations to what happens. But this is really what happens at the wall. The scattering problem that we do with students in the class is actually that's an artifact. This is really what happens. And then the particle, of course, k is small, so it's slow. But now this wave function turns back. It can't penetrate simply because the energy is too low. The potential step barrier is high. Of course, you could take a potential
and a little bit of tunneling. Is
not tunneling. It's going to die out.
The right side after this step.
Yeah, but it will not. This part will die out soon.
Oh, okay.
Not soon. It will take a long time to die out. But the infinite limit, in the steady state limit, which we use for calculation, that term is exactly 0.
Oh, that is your artifact. I mean,
No, that's not an artifact. That's again not an artifact.
That is a finite time phenomenon.
Not even that. That is exactly what happens at the boundary.
So this is a form of evanescent wave.
Yeah, that's an evanescent wave actually.
Okay.
And that is really what happens at the boundary. It's just that when what you're seeing here, the artifact is what you're going to see soon. This is nearly reaching the other edge. And now the fact that the other edge is held at 0 will make it bounce off the other edge. Slowly, because the k is small. Earlier the k was large, so the whole thing happened rather fast, but now you're going to see something more complicated happening. So this is what really happens. Now, of course, when it reaches this edge, you're going to see boundary terms coming. So that is why you will not trust this for a very long time. At least if you wait for a very long time, you're going to get artifacts not of your algorithm, but more because of the fact that you have a boundary condition. Okay? And maybe nothing is happening now simply because I've stopped. Is something happening? Yeah, it is something is happening. It's coming back. So that's a reflection from the wall at the other end. You can improve upon this. Of course, you can improve upon this by using smaller delta t's, smaller delta x's, more points. Stability will no longer be an issue. And using better algorithms, like instead of using the simple-minded.
But how can it reflect from the left end? Because potential is 0 there. There is no potential 1.
Potential is actually infinity there.
Infinity. That's how you made it. Okay.
No, I didn't do anything. I just put dead wall boundary conditions.
Oh, dead wall is acting like a potential.
Dead wall is essentially the same thing as putting an infinite value.
That means you are not updating that point. That's what it is acting like.
If I actually
boundary.
wanted to update this, I could use periodic boundary conditions. I could use other things.
Right.
Those would be more complicated to implement, but can be done.
No. Here it is not needed. Okay.
But you have to understand that the point is,
it is acting like a boundary, right?
It's acting like a boundary. It's like acting like an infinite frozen wall at the two ends.
Yes.
So if you really had a step,
because you are not allowing it to go beyond that, and
the way function is explicit is 0 outside. So that's exactly what you have in this infinite wall problem. So this one is going to override anyway on the size. Okay. So basically what I'm doing is using a potential which looks like this. So that's your step, but on the other two sides you have infinite walls. This is infinity here, infinity here. So basically your problem is confined within this. But that is simply because I want to be able to handle this with less difficulty. And of course you can improve upon your algorithms in other ways, but basically those things will be too complicated to do. But you can easily show off, say, things like tunneling. Instead of using a step, you could use a rectangular well and then show tunneling. But you saw exactly what happens at a step. It almost goes through with hardly any change if the energy is too big. If the energy is too small, it bounces back. It's still keeping on doing things now, but now you're getting interference between the wave packet which was traveling to the left and the one which is coming back. And of course, you are right that this is not. There are accuracies because of delta. There are inaccuracies which appear because of the delta t being not too small. I can use smaller delta t's, slow down this thing, and get more accurate results. But most of this, what you're saying, is not a numerical artifact. It's more like an artifact of the problem itself. In the long run, it's going to sort of settle down to a lot of tiny Gaussian wave packets. There are ways of understanding this, but I simply would say too much effort to put in. It's best to explain them away by saying that there are walls where there should be none. And because of the walls, you're getting this. Let me just try out something which I didn't do before. These were rehearsed before coming to give the lecture, because I didn't have the guts to just try it. And let's do something like this. So what we are saying is, when xs is less than 0, you replace it by 0. When it's more than 0, replace it by xs. I hope this works. Okay, sorry. Oops, my escape key is not working. Oh, sorry. I forgot about that. So basically what you're saying is, if the value of an element is negative, you replace it by 0. If it's not, you take that element. So now, basically what you have done is you put a triangular kind of potential. So that's what the potential looks like. So it's like a free particle on this side, spreading and so on, and then it encounters the potential. So if you confine the explanation to what happens when it encounters the potential, that part is perfectly accurate. You don't have to worry about, because it's a Gaussian wave packet, it has hardly reached the other ends. So this part is fine. There is something which would need a lot of complicated mathematics involving ID functions and so on to explain analytically, but it's pretty easy to see what's going to happen. Okay, so I think I will stop here. I've already gone half an hour over time. So if there are any questions, I can take them now.
Our pleasure.
So I'm through. It's up to Kishore now.
Where is Kishore?
Kishore has gone to sleep, I guess.
I see one question.
No, I am here. I am here.
Oh, yeah. You can
You see a
read
question.
some.
Where do you see a question? I can't.
In the chat box. Amit Kumar Bhattacharya asked, not asked, comment or asked.
What happens if you increase h? Does it still remain the same? Okay, that depends on. If you increase h, of course, your second derivative calculation becomes even less accurate. Okay. And then of course,
can I ask? Yeah. So the question really is that if you really increase the h, it becomes more and more inaccurate. So the spatial accuracy really worsens, right? So all the
spatial accuracy worsens, but at the same time, you can get away with using larger delta t.
So that's not my question. So the wiggles that you see, for example, if you
you're right. Some of those wiggles could be because of it's not entirely. So this is of course a numerical calculation. So it's not entirely a 100% accurate calculation. No numerical calculation is. So whenever you see competing problems, like there's an issue of reflection from the boundary. There's also an issue of reflection from the edges.
Yeah.
You can try using a smaller, but the point is if you use larger delta t, it's going to be even slower because you have to larger number of particles by decreasing the h. You are going to get into other trouble. But then you would be much better off not by inverting the matrix, but by using standard algorithms which are very straightforward for solving tridiagonal matrices. They're actually pretty straightforward algorithms. They're easy to code, and they're fast. They will at least help you recognize which part of the solution problem that you see is because of the boundary conditions, which part is due to the discretization. Okay. Of course, if you want to get more accurate results, you should use better algorithms.
This inversion of the matrix actually creates problem that I know for sure in the backward Euler that I've demonstrated even in the class. That you really get these wiggles, this Gibbs phenomena. But the problem is
but that's not the problem here. That's not the problem.
Yeah, that's the thing.
No, here of course there are numerical issues here, and backward Euler basically has this is stable, but it also has introduces errors of the other kind.
Yeah.
This one at least Crank-Nicholson is sort of best of both worlds, staying within simple enough algorithms. There are of course other algorithms based on say the Baker-Campbell-Hausdorff formula and
implicit explicit mixtures.
mixed algorithms.
Yeah.
There are plenty of other things. For example, even the second derivative calculation, you could improve upon that by using higher order derivative approximations.
Yeah, that's true.
You can do many things, but
we showed
I would
even
say,
for the wave equation, like we can use the third order upwind to directly show that even like a Gaussian wave packet really stays. This is what we have demonstrated also in the class. But even the artificial diffusion actually comes in if you use a simple finite difference, just like the one that we
that's
used
exactly
here.
the point. And as you rightly point out, this is the CFL condition. This is this stability condition. And it's very easy to work out because this matrix is a trivial matrix to diagonalize. To find out finding all the eigenvalues of this matrix is really very simple. Because of the simple structure which the matrix has. It's just a 2 lines of calculation will show you that the eigenvalue, the largest eigenvalue becomes bigger than 1 unless delta t is very small.
Any other questions from the participants?
And by the way, the CFL condition is almost exactly the same here, simply because it is the same equation. Consequences may be different, but heat equation and the time-dependent Schrodinger equation are basically the same kind of equation as far as the mathematical structure is concerned. They're both parabolic differential equations, same kind of stability issues, everything.
So just let me ask you one more thing. Is that, are you saying that rather than using any Fourier sort of methods that usually even for the complex problem like Navier-Stokes and so on, like a method like this can be better to handle the temporal part?
Not really. Frankly, no method is perfectly good for everything.
I see.
Usually, it's always better to have a lot of methods. If you are really wanting to do, say, research level work, for example, then it would be best to have a lot of methods in your repertoire and try back and forth between them. Of course, with some mathematical guidance as to which one works better where. It's not just random back and forth, but it's important to understand why the algorithms work, they do, why they don't when they don't work. Okay.
Yes. Okay.
So that's also important, I guess, to also drill into our students, because some people have the idea that computers can solve everything perfectly. So what's the point in learning anything? That's one option. The other is since computers have all these errors, what's the point in computing? These are two extreme viewpoints which students have, both of which are, of course, wrong. But you have to sort of point out that by judiciously bringing in other information which you already know, you should be able to work these things out.
If there is no other questions, then let's thanks to the speaker. Lovely presentation as well as illustration. And now this is the time for vote of thanks. Dr. Dolunchapa Saha, please.
Thanks, Kishore. On behalf of the Department of Physics, Prabhu Jagatbandhu College, firstly, I extend my heartfelt gratitude to Dr. Abhijit Kaur Gupta and Dr. Ananda Das Gupta for their sheer love of teaching. They readily agreed to our proposal. The team, as usual, has guided us through Python programming for quantum mechanics practical of present 5th sem this time. The lectures were lucid, very interesting, and very interactive too. Thank you, Abhijit. Thank you, Ananda. I thank our audience for their wholesome support. The teachers, the researchers, and students for your participation through this 3.5 hours. Thank you all. We appreciate your support very much. I hope this workshop has enriched you. I thank our principal, sir, for his spontaneous support in this endeavor of ours in a very short notice. Dr. Promita Howle, thank you for your sincere cooperation. And lastly, I would love to thank Dr. Kishore Mukhopadhyay for initiating and single-handedly managing this workshop. Kishore, you took a very timely drive to help us all who teaches Python for semester 5 for this physics honors course. Thank you for your hard work. With this, I would like to declare closure of this workshop. Thank you all once again, and a very good evening.